going to wait for anyone to come in. So for anyone who's in, you're probably wondering why I'm taking some time, just waiting for some, if there's anyone else coming in before I started. Let's see, it's 9 p.m. Eastern time. All right, I think we can get started. Welcome back to STEM Online Academy. I'm glad you're here tonight. All right, very glad you're here to join me. It's going to be an interesting night. So what we're going to talk about today is oscillation integrals, okay? And exactly why they're so, scary and, all that stuff, right? Why they're tricky to deal with, right? In a calculus class, right? Now, technically, they look scary to approach or try to solve, actually. But in reality, the reason why a lot of students have trouble with these types of integrals is because of the fact that they don't have a natural fluency to them that we're used to seeing, right? A certain method that we know how to, approach and calculate, okay? When it comes to these integrals, we're going to do some interesting stuff. Oh, good. We have a new person coming in. All right. If you could put in the chat a thumbs up or here or whatever, that would be great. Just to let me know that you are cooperating in this live show, okay? All right. Now, as I said, oscillation integrals, right? They can be technically annoying, but in reality, they're actually straightforward to deal with, right? They're not as scary. Just as I said, it has to deal with the type of integrals that we're used to, right? We expect them to spit out a certain answer, okay? So what I'm going to do is, right? We're going to look at tonight, we're going to look at exactly why these integrals are so complicated, and we're going to slow this way down. The goal is not to just calculate some integrals fast, right, and just compute it. The goal is going to be to figure out why the oscillatory integrals behave the way they do, okay? And when I mean behavior, I'm talking specifically, right, specifically about why there's maybe an increase in amplitudes or a decrease in amplitudes, that type of stuff. Okay, let's see if anyone else is coming in. Let's see, is anyone else coming in? Let's see. Right. Okay, so an increase and decrease in amplitudes and stuff like that, decays, all that interesting stuff when it comes to oscillatory integrals from a geometric and physical point of view. Okay, which is I think very interesting. You'll find it very interesting as well. Okay. Right. So as we're doing that, right? So as I mentioned, goal is not to just do the calculations. The goal is going to be, right, to understand why these oscillations work in the first place. Okay. Right. It's going to be a symmetrical way of thinking, you can say. All right. Now, so if you've ever had an integral, for instance, right? Let's open the whiteboard. Okay, so let me share the screen. Okay, let me share the screen now. All right, and we're going to the whiteboard. Okay, so as I said, we're doing oscillatory integrals and also their applications. Okay, so if you ever seen an integral like this, right? This is what we're going to be looking at today. This integral right here. Integral sine x dx all over x, and you've always wondered, does this integral converge, right? I'm sure in your calculus classes you've done convergence and divergence of integrals in series, but I bet you've never thought that you can have an integral as strange as that could be evaluated, right? It turns out you can, right? And it turns out you can determine if it converges or diverges, okay? So yes, if you want to figure out if an integral like this converges and why it does, you're in the right place. Again, we are going to approach this from a geometric and using geometric reasoning and physical reasoning as well to understand how oscillatory integrals work, okay? right? So let's look into that. Right, just 1 second. Just trying to find, because we're going to do quite a few things here. I have a checklist. Okay. Okay. So we're going to do exactly that, right? So this session is going to be purely for students, for undergraduate students in mathematics, physics, or engineering, right? Who want to build real intuition. Okay, that's what this session's about, right? Not just practice tests that you want to memorize, but all sorts of divergent ways. Divergent ways of thinking about calculus and its applications. Okay. By the way, if you're in the lecture, please put something in the chat. It will be appreciated, so I can have a back and forth conversation with the audience. Okay. All right. So please let me know, thumbs up or anything. Please let me know. Okay. It'll be really, really helpful. All right. So we're going to use all these techniques to evaluate the integral, as I mentioned right here. Right? And we'll talk about the general form of an oscillatory integral anyways. Okay. So let's go to that. Let's discuss things on oscillatory integrals. So we're going to be looking at this type of integral. Okay. So as I mentioned, we're looking at this example, right? Or this question, if you want. Let me see if anyone is inside. Okay, yeah, we have 3. So we're going to have this question right here, right? It's a question. So it's a question. Question. Or I should actually put like this. Sorry. I'm going to look at the first example. So example 1. I'm going to say example. I can't write today. Example. Okay. And the type of integral we're going to be looking at is this integral right here. Okay. So I equals the integral from 0 to infinity. Okay. 0 to infinity of sine x dx all over x. Okay. We're going to figure out, not by calculating it specifically. I have another video where I've actually calculated this specific integral from my book, actually, from Advanced Integration Techniques, right? That was in another stream. In this live stream, we're actually going to figure out that actually gives us that it actually converges, okay, without doing any calculations. All right. So that's exactly what we're going to deal with here. Okay. Right. So how do we know based on this integral if it converges or diverges? Okay. Without doing any calculations. Okay. Anyone tell me? Anyone know why this integral is going to converge? Why would it converge in the first place? And how do we know that? Put things in the chat and let me know what you think about the integral. How do we know that this integral is going to converge, right? How do we know that this integral, sine x dx, is going to converge? Now, how do we know that? Is there something about the sine function or sine x over x that tells us if this, if there's something about the function, you know, because it's a periodic function? That's a hint. It's a periodic function, right? So just to jog your memory, right? Over here, let me just make a graph, right? Okay. All right, so we have something like this, and then we know that sine x is like this, right? Right, this is y equals sine x, correct? This is y equals sine x, right? It's a periodic function, okay? So how do we know if this is going to converge or diverge? Anyone here, let me know in the chat. So first off, just because the sine function, right, is the way it is, right, you can see it goes from increasing to decreasing, increasing, decreasing, increasing, decreasing, right? Now, the function itself, right, so the way to determine if something converges or diverges is not dependent on its size. It doesn't depend on the size of the function, okay? So number one, make sure that you understand that it doesn't have to do with the size of the function whatsoever. Okay, so the size of the function does not determine if the function will converge or diverge. All right. Right. So the growth measures how large, right, something gets, and pretty much the oscillations. I think it's pretty obvious. There's oscillations here. It's a periodic function. Is going to control how the function is going to be alternating. Okay. So if you have a function like sine x, as I mentioned, that's why I graphed it here, because it's a sine x part. The sine x part of the function, let me highlight here, is probably the most important, okay? All right, so the sine x part of the function is the most important, all right? And it mainly has to do, right, the fact that a function like sine x is never going to get smaller, right? But it changes regularly, right? And how does it change? How does it change? How does sine x constantly change? It's because it's alternating, right? You can see the function is alternating, right? It goes to a maximum there, right? So there's a maximum. We got a maximum there, minimum here, and it goes back to up to a maximum, and back to a minimum at the bottom. Okay, so you can see that there's a constant alterations, right? So that sign changing, right? So you can see that the sign changing is creating something here. Okay, it's creating something interesting. So the sign changing, okay, it's creating something interesting with the flow of the function. Okay, all right. So that changing structure causes systematic, right? A systematic cancellation, pretty much, when it comes to the magnitude function, right? So that constant cancellation, there is a cancellation, right? If you highlight here, what I mean by cancellation, I mean like cancellations of these curves here, right? So if I were to highlight the upper part here, right? If I were to shade it in like this, okay? And then the bottom part over here, right? That's what I mean by cancellations. So you can think of this also physically as well. Like if you had two upper and lower crests, if you ever done a physics course before, right? You have one going in this direction, one going in this direction. Their maximum and minimums cancel out, right, if they were to come together, because there's a node that comes here, right? So there's some physical intuition here, all right? So that's another way to explain it, okay? So you can see that our function y equals sine x, right? The cancellation of the upper curve and the lower curve, because of the maximum and minimums, creates a very interesting structure. Okay. All right. So 1 second, I want to see if anyone else is here. Anyone else coming in? Right. Yeah. So it's going to be constant systematic cancellation, right? Over the entire interval, right? Over these long intervals, right? Maybe this is going from 0 to 2 pi, for instance, right? So constant cancellations, maybe one over here. I'll highlight it with something else, okay? So let's say we have green here, right? This one's green. Maybe let's use a different color to differentiate from the x-axis. Sorry about that. Right? So you can see there, constant cancellations, all right? And you can see how the growth is affecting here, right? So let me actually go from just a regular graph to a mathematical model to show you what's happening. Okay, so I'm going to go to a mathematical model that I have here. Okay, so I'm going to stop sharing. And we're going to go to see a model that I have. Okay, so we have a model here. Okay, we're going to look at this model. And then I'll share a screen again so you guys can see it. All right, so I'm going to share a screen. I'm going to share my screen. Okay, let me see here. Yeah, there you go. I'm going to share it. All right, you guys should be able to see the model. So the integral from 0 to infinity of sine x over x with respect to x, we're going to visualize how the convergence is happening. Okay. So if you can see here, right, carefully, right, f of x is equal to sine x over x. Okay, that's the upper curve, right? The bottom curve, a separate graph, we have integral from 0 to L, okay, where L is the length of the interval of sine x over x with respect to x, okay? Now, I may need to explain something here. The first graph is for sine x, right? F of x equals sine x over x. The bottom graph is the integral, okay? Now, can anyone tell me what these graphs mean here? Specifically, what do these graphs mean? Okay, so what's the point of this? I paused it for a reason. Can anyone tell me the behavior, why this behavior is important? Anybody know at all why this behavior is important? Okay, please let me know. It's always helpful if I have a connection with the audience, back and forth connection, right? It is a live show. Please tell me why these curves are important to showing convergence. Well, you can see the upper curve, right? If you guys don't know, the upper curve is sine x over x. That's just a regular graph, okay? And the orange graph there, and there's a shaded region of the orange graph, right? Below the curve in the first part, the upper part there, below, up, below, and so forth. And you can see that it has a very interesting type of oscillation, okay? It's not exactly a straight type of periodic function as you normally have seen, like in the sine x function, it's sine x over x, okay? And then if you compare that to our second graph is actually graphing the integral of sine x over x dx, okay? If you were to take the graph, right, of the integral, as I just mentioned, right, you can see as L, right, as capital L, capital L is the upper bound of the integral. Okay, so as you can see here, right, the upper bound of the integral from which is L, right, is going to infinity. Okay, so again, let me show you something here. Right, as you can see, is that as L approaches infinity, right, our integral, right, will converge to pi over 2. Right? Right? Any questions on that? Any questions? Please let me know. Okay. By the way, I always bring up models and graphs and stuff like that, specifically simulations of models using programming, because I feel like it helps bring the math alive. Otherwise, always doing chalkboard work can get boring, right? If anyone is wondering why. So please let me know if you're understanding this conceptually. Let me know if you're understanding this. I want to make sure that you guys are on speed here with this. Okay, let me know if you guys are on speed, right? Don't be shy, ask me questions, right? It's supposed to be a live show. It's supposed to be a back and forth type of thing here. All right, so as I mentioned before, right, since we have both curves, okay, the point of this is to show, right, that we're getting convergence, and we're getting convergence is the fact that the lower the lower graph there, that integral there, right? As you can see, right, we've reached a limit at pi over 2, okay? We know already that this integral, sine x over x, of respect to x, already automatically gives us an answer of pi over 2. That can be proved. You can watch my other video for that. I have a live video and also a stream on that, on how we get pi over 2. But the fact that it gives us a number, we know that it converges, right? Now I'm proving this graphically in this live stream, that you can get convergence, right? Because as this integral here, right, from 0 to L, right, as L approaches infinity, that's the upper bound, right? Our upper bound is infinity of this integral, right? Sine x over x, integral of sine x over x dx has to converge, right? Has to converge to pi over 2, right? Okay, because the oscillations are just going to be canceling, right? Such that the area, right, is going to pretty much settle, right? So you can think of this as, this is like a pi over 2 or a 90-degree 90-degree oscillations, you can say, pretty much, right? Okay, so that's what's happening here. Okay? This can be a little tricky to intuitively understand. Okay, it's a skill, it's a hard skill, but if you can understand things not just algebraically, but also through a visual spatial approach, then this can really help you mathematically understand things at a comprehensive level, both in at a calculus point of view, but also in the visual spatial point of view, right? So let's continue, right? Let me show you. Look here. Let me show you exactly here. So we have this. Now let's continue the simulation. Right. So as you can see here, again, I'm going to show you the entire simulation. We have the upper curve there, right? Right. And we're just trying to visualize the convergence of the integral, right? So as you can see here, as L is approaching infinity, right? Right. As L approaches infinity, at the same time, our integral, by the way, limit is not L, limit is what the value of the integral is pi over 2, right? And our simulation proves it. As you can see, that point particle, let's call it, right, along the blue curve there, is traveling along, and the max value, which is pi over 2. All right. All right, so let's look at it again. I'm going to try multiple ways of explaining it because it does take a while to, geometrically understand what I'm talking about. Okay, so just one sec. All right, so we have, again, what I was saying is that growth, right, measures how large a function gets, right? But oscillations, right, are going to control, right, how they're going to alternate, all right? So that's one thing that's very important, right? Now, what students are getting confused with is that they think that the size of the function is going to determine if it converges or diverges. This is not true whatsoever, okay? So a function like sine x, for instance, is never going to get smaller. It's just going to be changing regularly. And that's changing regularly, I mean, is the alterations, right? It alternates, okay? Now the sign changing, right, is going to change the structure of the entire systematic cancellation of the function over a long interval. Okay? I think that would make sense, right? So I'm trying to explain this way. So over a long interval, the systematic structure is going to be changed. Okay. Right. If there's any questions on that, please let me know. I want questions. Please let me know. All right. So that's what we've got right now. Okay. So that is one thing, one area that we're going to be trying to understand a bit more. Okay. Is understanding graphically how functions behave, right? without calculating them all the time. Because quite often in calculus, as you know, that's not always about getting a definite answer. You also want to know the behavior, the convergence, the divergence, the all this stuff is really important. Okay. All right. Now, there's some key concepts I want to be able to reframe here. Okay. I just love playing this over and over. I think it's really fun. Okay, so let's see here. Let me know if you have any questions, guys. So you're going to notice, right, that the function itself, okay, as I said, right, growth is going to ask how big, right? So how big the function, the function are in terms, right? And the oscillations, right? The oscillation asks, how does, right, positive and negative contributions, contributions interact with the function, right? So again, what I'm saying is that the growth, right? Growth would be asking how big are the terms, and the oscillations would be asking how do positive and negative contributions would be interacting. Okay. Let me see if anyone is there. Let me make sure. Oh, we got 5 people. All right. Hi, guys. Please let me know in the chat. Interact with me. Let me know what you guys are a little about yourselves, or you can put something in the chat. Maybe put I, H, or thumbs up. Thumbs up in the chat. Please let me know. Okay. So again, we're just looking at evaluating an integral. For those of you who are coming in, we're evaluating an integral from 0 to infinity of sine x over x with respect to x, and trying to understand why this integral actually converges. Okay. Why it does converge and why it doesn't diverge, right? Okay. And we can do that based off not just by calculating it, right? Calculating the integral. I mean, quite often you have to do that. And I did it before in another video. You can check that out. But here I'm just 100% geometrically trying to understand the behavior of the integral. So you can get certain behaviors from the graph. They're not always easy to extrapolate, though. But I'm going to try and help you guys be able to extrapolate important information from the graphs, right, in order to know when a function is converging, diverging. All right. So those of you who are just coming in. All right. Now, another misconception that students have that's not clear is that if they can't bound it absolutely, if they can't bound a function absolutely, then they get confused. Okay. So what do I mean by bound? Bound, I mean like you put some bound, like some sort of constraint on the function. Okay. You should know. I don't have to go into detail about them. You should know what I mean by that. If anyone in the chat can tell me what I mean exactly by bound. Okay. So by bound. What do you mean by bound? Okay. So what I mean by bound is putting a constraint. So quite often students who don't know, or, they have a function that they can't bound absolutely, they assume that the function, not assume, but they will just get completely thrown off, right? So just because you can't bound it doesn't mean that, that you're going to have something that diverges or converges necessarily. You just need to be able to think clearly on the fact that if contributions cancel geometrically, right, then what ends up happening is that the computation is unnecessary. Okay, so again, if the contribution cancels geometrically, then you don't actually have to calculate the integral to figure out if it's actually converging or diverging. Okay, so there has to be some sort of symmetry to the cancellation of the curves, as I'm saying here, right? right? It's just like having a node and an antinode in physics when they come together, right? The crest and the the crest and the troughs when they move in the opposite directions. One has you know, it's a crest and a trough. They cancel equal the amplitudes, opposite directions. They cancel to create a node. Think of that being applied here. So I'm using both geometric and physical reasoning to explain the argument of why this integral actually converges. Right? So if there's that type of symmetry of cancellations of the functions, then you can figure out actually that if it converges or diverges. Okay. I'll be right back, guys. I have to go to the washroom. Be right back. All right, guys, I'm back from the washroom. All right. We have some new people coming in. Let's see. All right, not ready yet. All right. So as I was saying, I was just explaining exactly how this interesting function works, right? And why it's converging in the first place, right? Right. So as you can see, right, again, I know I've been showing this mathematical model for a while, but I just want to rewind here, okay? So if we can rewind a bit, notice how the orange curve goes from a max and then it goes all the way down, okay? And at the same time when that happens, you can see the blue curve of our integral is from the bottom and it goes all the way up to a max, right? So you can see that there would be a cancellation there, right? And then the orange alternates going to a minimum, plus the blue alternates to a max, right? And then blue minimum, orange maximum, they're almost overlapping. So there's a cancellation, right? So when you see symmetric cancellations like that, you can tell you the behavior if the integral converges or diverges. Okay. All right. Please put a thumbs up in the chat if you're enjoying this. I like to make my videos interactive, especially with modeling. Okay. Also, tell me what you think about the model. That will be handy. It's handy to get feedback. As you can see here, both curves, as I said, right? There's a cancellation, right? Now, you may be asking, yes, when we have to deal with figuring out if an interval converges or diverges, this method can be very handy, you're thinking as well. It is, but you're probably also going to ask a question such that, okay, but it doesn't give us the answer. What if we need to calculate the answer? Well, if you need to calculate for A or B reason what the value is, integrate normally. When I mean integrate normally, you use methods that would make sense, obviously, right? Okay, and that will give you actually why the limit is pi over 2. Okay, so this simulation, this mathematical model that I've made here, will not automatically tell you that it's pi over 2, just to make sure you're understanding. Okay, is it's going to tell you that it converges. Okay, it tells you that it converges, right? So this tells us the geometric behavior. To calculate the pi over 2, you can't do it from here. You'd have to actually do an integral and calculate it, right, step by step. Okay. All right. So let's go back to sharing. Let's see. Okay, let me stop share. I'm going to stop share. Let me stop share for now. Okay. And then we're going to go back. Just one second, guys. We're going to go back to the whiteboard if possible. Okay, whiteboard. Not yet. Just 1 second, guys. unless you guys can see it right now. Easy desktop. Okay, let me just get back. Let me just get back to sharing. Okay, let's get back to sharing. Okay, we're going to go to the entire screen. Just give me a second. Technical difficulties. All right, so we're going to go to the whiteboard. So I was explaining exactly why this integral is converging or converging in the first place. Okay, so how sine x, integral sine x dx over x, why it was converging in the first place. All right, I want to ask you guys, since I've been mumbling, it's a live show, I need interaction, right? Since I've been mumbling, can you guys maybe, you can ask me questions, right? Same time, ask me any integrals that you have difficulty with, right? Please ask me integrals. You can interrupt me at any time, right? It's not a big deal. Okay. I like having a back and forth conversation. Okay. All right. So let's continue. So as I said, right, what I was saying earlier, right, for this type of function, right, is that pretty much this is what I was saying. Okay, just that's another way of explaining it. I have multiple ways of explaining the same thing to make things easier conceptually, right? So think of the upper region here in red being positive area, the bottom being negative area, okay? And this constant oscillation and alternation of positive and negative areas, positive to negative areas, is what actually makes this function very interesting, the sine x over x, okay? Right? Sine x over x. Sorry, sine x, because we're looking at sine x, right? The positive negative alterations. So this one sec, someone's coming, asking a question. Right? So in other words, what I was saying is that when you add, right, when you're pretty much adding, right? So when you have pretty much each oscillation having a positive area and each oscillation followed immediately by a negative area, you're pretty much getting these areas, relative to their spacing is going to give us pretty much, like alternate slices, right? Right. So alternate slices that automatically increase, right? That will increase and neutralize each other, right? It's like having a node and antinode, as I mentioned, right? So I hope me discussing all of this, like I really discussed this comprehensively from every angle. I hope this is making sense why this function is converging, why that integral of sine x over x is converging. Okay, please ask me questions. If you ask questions, it would be great. And sometimes it doesn't have to always be mathematical. It could be what you want to talk about. Okay. All right. So that's what's in the game today, right? So this integral is really, really, really neat. Okay. I'm going to look at. I want to see our list. What else we're going to talk about? I had it down. Just want to go back to my list here because we're going to talk about interesting stuff, right? We talked about why oscillatory integrals, right? Why oscillatory integrals are important and why they matter, right? So here's my checklist, right? Core problem, oscillation versus growth, visualization, cancellation, why this integral converges. We've talked about that. Frequency, phase, and dominant behavior. Pretty much we were discussing that, right? I think we were, right? By the way, if anyone is confused right now, what I mean by frequency, phase, and dominant behavior. What do I mean by frequency, phase, and dominant behavior? Well, we already talked about it, right? When I was talking about giving all those different explanations of why this integral converges, frequency, just behaving as a wave, right? The sine function is behaving as a wave. Phase, if the curves are in phase. So, for instance, if you have, like a symmetry to the curves, right? That's what I'm talking about, right? Symmetry, and they're traveling at the same rate. So let's say you have one function like this, right? One function like this, right? Another function like this, right? So let's say they're in phase, right? This one is overlapping with this one. This one's overlapping with this one, right? So it's overlapping with this. This overlaps with this, right? Like the curve on the top and the curve on the bottom have a maximum and minimum that are overlapping. Okay, that's the type of thing I mean, right? And dominant behavior. Okay, is there any questions on what I'm talking about? Any questions at all? We discussed why it converges as well, right? Basis and dominant behavior. So we did quite a bit. We're going to be looking at possible applications. Okay, unless anyone wants to stop me right now for questions. Okay, anyone want to stop me at all? Right, because we're looking at, just like we're going to look at the applications of this integral. Actually, before we look at the applications, I know I said I wouldn't calculate the integral of sine x dx over x. I already did another video on it, another live stream. This, as I said, this live show was mainly to look at oscillation integrals and how they behave, right? But maybe for homework, if you want, anyone can try this, okay? So try for homework proving that this is equal to pi over 2. Okay, so prove for homework why this is equal to pi over 2, please. All right, so try that for homework. For those of you who don't know or haven't tried it before. Okay. So let's get back to it. We're going to be looking at, okay, let's get back to it. So we've looked at the behavior of this integral. And this is a type of oscillatory integral, okay? But there is one problem. I haven't defined what an oscillatory integral is, okay? But most of the times, students assume an oscillatory integral is anything with sine x or cos x because of the periodicity of the function. No, that's not what an oscillatory integral is, okay? I'm going to define what an oscillatory integral is. And this integral is fundamental. I'm going to define it how, applied mathematicians and physicists define it, right? It's not really thinking pure mathematics, but its applications in physics are very important. Okay, so I'm going to define it in a moment. Okay, so what pretty much the mathematical framework of an oscillatory integral is. Okay, just one sec. Okay, that wasn't it. Just want to make sure we're on schedule. All right, so let's look at our oscillatory integral that we're going to be looking at. Okay, so we're going to talk about how. Let's see what's in the comments section right now. Not right now. Okay, so how physicists and let's how physicists. I should say and, but how physicists reason Yes, reason. How they reason about waves. About waves. Waves. I think we're also going to cover diffraction as well. Diffraction. Diffraction. That's where this integral, this type of integral I'm going to define, is used a lot. Diffraction. And diffraction works, okay? So that's what we're going to be talking about. Okay, so this is going to be like a title. All right, so first off, as experts, physicists never ask, pretty much, they never ask, does this integral converge? Okay, that's not what they ask, right? Their job is not to be mathematicians, right? So from a physical framework, they would never ask if this integral converges or diverges. They don't give a damn about it. Okay, they would just they would ask in terms of does it destructively interfere or constructively interfere or whatever. Okay, that's what they care about. All right, they care about if that integral is going to be constructive or destructive. Okay, now quite often, as I said, scientists wouldn't really be. Usually they wouldn't have, well, they deal with integrals. They're applying math, but usually they're looking at a system or a phenomenon that they're interested in seeing if it's constructively or destructively interfering. Here, though, they could also end up having it the reverse. What I mean by that is mathematically they may have an equation, and then they can interpret if that integral or that function or that equation actually has any destructive or constructive interference, which is pretty interesting, right? It's like going backwards, right? In mathematics. Not backwards. This is for mathematics and physics, but you can do the other way around, physics to mathematical reasoning. Okay. So they would never ask if the integral converges. They're just curious if it, constructively interferes, destructively interferes. Okay. Any questions on that? Okay. Now, I do want to mention, right? I do want to mention that when it comes to waves, right? When I mean waves, we're talking about waves both from a mathematical but also a physical lens as well. But if we're talking about waves when it comes from a physical lens, right? Physical approach is that the contributions with different phases will cancel. In other words, I'm saying if you have particular wave fronts, okay, right? I know I'm getting a bit scientific here. Sorry about that. Because you have you have wave fronts, for instance. Okay. Here's the graph, for instance. You have waves like this, and like this, right? Now, obviously, those waves, one has a crest and trough, and they'll create a node, right? Right. What I'm talking about here is if you have a wave, the contributions with different phases are going to cancel. Okay, so if you have different phases, they're going to cancel. Like what I was showing you earlier about the sine x over x function, right? Right. There, in that mathematical model that I showed you, that those functions, right? That function, sorry. When we compared the two graphs in the simulation, right? You can see that one curve maybe had a maximum in that phase, while the upper graph, the upper curve, at that same phase had a minimum, right? And then reverse, max, min, max, right? So they're in phase, but equal and opposite. So those are cancellation. Okay, so different phases cancel, right? So I want you to know that when it comes to waves, contributions, right, with different phases will cancel. Okay, so it contributes to different ways to cancel. But only regions with stationary phases survive. Okay. I think it's pretty obvious, right? If you have different phases, right? Like this is a classic example, right? They come together, equal and opposite in their magnitude, but one is, like has a crest here. The maximum is a crest. The trough is a minimum for this one. They come together. They cancel. It's destructive, right? Okay, that's what I mean. Any questions? See if there's any questions. Any questions? Yeah, please let me know if you have questions. I like to interact with the audience. Okay, so that's one thing when it comes to one very important thing of how to reason about waves, not just mathematically, but also physically as well, right? Because there's a lot of applications physically. Okay, now I'm going to talk about the formulation of the oscillatory integral. So the oscillatory, let me put it here, the oscillatory. I'm going to use a different think here when I say the oscillatory, use yellow, sorry, I think yellow is more important. The oscillatory, oscillatory, I'm going to use green, too much blue. The oscillatory integral. Oscillatory integral. Integral. Yes, there's a general formula for it. Okay, so let's look at that. So there's a general formula for the oscillatory integral. Okay. And it also serves as a very good hint on how this is actually really deep and very ingenious way of explaining of how to solve an integral of this nature. Okay. Right, so the one that I assigned above for homework to prove that it's equal to pi over 2, why, like how to solve it in the first place. It's been defined as an oscillatory integral. But why is it an oscillatory integral? What is an oscillatory integral? It's this, okay? An oscillatory integral is anything of this nature. So definition, DEFN for definition. Okay, so an oscillatory integral is the following. If you have an integral I, it is equal to the integral, right? Integral of, right, e to the I lambda x, right, times f of x dx, where lambda is an interesting value there. Right? It's a constant. It's not a function. Okay. All right. So don't get that confused. But any integral of this form, okay, is automatically an oscillatory integral. Note this is defined as an oscillatory. So this is defined as an oscillatory integral. Is known as an oscillatory integral. Okay, so that's what an oscillatory integral is. All right, any questions? Anybody? All right, so we now know what an oscillatory integral is, how it looks like, its form, and its importance. Okay. All right. So I wanted to mention, okay, for that problem above, there's an interesting hint that I'm going to yield here, okay? So page 3, for those of you who want to solve it, here's a major hint. I probably have to give you this hint because even if you apply certain mathematical techniques that you know or need to look up or whatever, you may still have a lot of trouble doing this, okay? So let's look at that. But the point is to push your boundaries, push the boundaries of your reason by applying, by applying yourself and challenging you, right? All right. So let's look at this guy here. Okay. So if we have, so I'm just put hint. I'm highlighting hint. Very important hint. Okay. If you look at, so I want you to apply. So apply. Apply a combination. So apply a combination. So a combination. This 1 second. Apply a combination of Feynman trick. I'm going to highlight this. Use blue here. Feynman trick to solve that problem I assigned for homework. Feynman trick. It's 1 n, not 2 n's. Jewish names have usually 1 n. German has 2. I always get them confused. Yeah. Jewish names have 1 n. I think German has 2 n's. Yeah, I always get that confused. Anyways, so Feynman, right? So Feynman trick. Okay, so apply Feynman trick. Okay. If you don't know what that is and you're really interested in learning this, how to solve this integral, refer to another live show or stream earlier in my YouTube channel. It should be somewhere there. It's not used to be able to find it easily. It's on Feynman trick, purely on Feynman trick. I talk about the definition, all the theorems and everything, and how to apply it. So apply a combination of Feynman trick with plus definition of what I just mentioned right now, the actual formula of an oscillatory integral. So apply what an oscillatory integral is. Okay. So apply. So I'm going to say here, apply plus apply the formula, right? So apply the formula. Why come I'm writing this better? Apply the formula. The formula of an oscillatory integral. Okay, any questions? All right, so you're going to apply both. All right, so just to let you know, the problem that I assigned you guys to do for homework is that I, right, just to let you know, I is equal to the integral, right, integral from 0 to infinity of sine x dx all over x. How to calculate this integral. Okay, so apply Feynman trick and the definition of an oscillatory integral that I mentioned on the other page. This guy right here. Right, integral of e to the I lambda x power times f of x dx. Okay. So the fact that anytime I already gave you a hint, a good hint, I have to give you hints for this because this is not an easy integral to intuitively know how to solve, right? Elementary techniques don't work. You have to know what Feynman trick is. So look that up in the YouTube video if you don't know, or other references or books that you have. I can recommend some books. I can recommend anything if you want. Just let me know now. Okay. All right. And you have to apply the formula of an oscillatory integral. Okay. So apply that as well. What the definition of an oscillatory integral is, I put it over here. Okay. Right. So what you would do is, right, you'd obviously treat, your f of x as sine x over x. Okay. So if x is your sine x over x. So try this for homework, a combination of both. All right. Okay, so I was talking about, I want to get into, if possible, any physical application of this. Now, I'm not going to come up, I don't know specifically why. I know the physical application of this, right? Because I put it, this integral's in my book, by the way, okay? But I do talk about the physical applications in diffraction and wave interference, for those of you who like physics as well. It does have applications in those. So any type of diffraction, wave patterns, or wave interference whatsoever. Okay. Just 1 second to see if anyone's coming in. Someone coming in now? No. Okay. So let's get back to it. So we're looking at combining both this and this, right? All right. Now, an oscillatory integral, as I defined it earlier, right? This is still relevant. An oscillatory integral, as I defined earlier, is mathematically, I gave its definition. Okay. Now, physically, though, right? We still use that same definition. Integral e to the I lambda x times f of x dx. Okay. Now, this integral is it has a lot of interesting properties. I'll let you know about that, right? And quite often, when you can't solve an integral, normally you may need to input a function of this nature. Okay, right? But yeah, let's get into the physical application of this. What I mean by it. So, and the physical intuition behind this integral. Okay, so the key physical intuition, right? You should know, and that's very important, right? Is that this dives directly into diffraction, interference, wave patterns, signal filtering, and all of that. Okay, and also something else, something called Fourier transforms, which I talk about again in a past lecture or stream. So again, you're going to, if you don't know what I'm talking about, right? Especially with the problem I assigned earlier for homework, please refer to other videos, live streams, or streams in general as soon as possible. Okay. All right. Please give me, please look at other streams and live shows as much as possible, because that's the only way this is going to make sense, right? But you have to fit things together. Okay. You have to be able to pull from here, and make the connections, right? I'm not always going to be solving the problems like step by step. In a lot of videos I do, but in live shows, I find it's handy when there's a back and forth. So if I am going to solve something explicitly that requires explicit computation, it's good when I get the feedback from the audience to make sure they're understanding as well. Okay. So yeah, this integral, the oscillatory integral, oscillatory integral, has applications of diffraction, interference, signal filtering, Fourier transforms. Right? Obviously, Fourier transforms. Right? You can see that this looks like e to the I omega t times f of t. This is a Fourier transform. The only difference is if Fourier transform is bounded from minus infinity to infinity. But anyways, I digress. Look up those that specific topic on Fourier transforms, if you're understanding what I'm saying. But the point of my streams is to show you the connection between a lot of different topics, which utilizes both, your applied mathematical skills, your logical skills, and your visual spatial skills, right? Okay. Now, I want to go back. To this actually. I was talking about earlier. This integral again. Yes, we spent the whole time talking about this integral, but there's lots to talk about this integral when we break it down conceptually, anyways, as opposed to just only calculating it. All right. Right. This is something that students need to clarify. Okay, the convergence. Right. Now, I explained it earlier with a simulation, okay? But I want to go back to it because I feel like maybe whoever is watching now or maybe is going to watch it later, not always anyone sees live shows, you may not be able to understand it still. So I need to explain it from another angle, okay? Good teacher always explains from multiple angles, multiple perspectives. Okay, so I'm going to explain it from another angle. So this is a moment where students need to clarify something, okay? One way to analyze this, okay, if it converges or diverges. So let's look at another graph here. I'm going to make a graph like this, okay? XY axis. And I'm going to pay attention to this part of the function, okay? There's a 1 here, by the way. In order for that to be sine x, that's 1 by sine x over x. I'm going to look at 1 over x. Now, why 1 over x? What is so unique about 1 over x? Why would I want to analyze that? Why would I analyze 1 over x? One over x has something unique to it. Okay, let's draw something here. So we're going to draw a graph of 1 over x. You know that the graph of 1 over x, you used to know this is basic algebra, is something like this. This is grade 11, and even grade 12 algebra. Okay, it's not exactly accurate, but, and there's an asymptote, a vertical and horizontal asymptote to 1 over x. Let me put it over here. Okay, so it's so we have a vertical asymptote here, right? At x equals 0. Okay, this is at x equals, just 1 second, guys. X equals 0. Another one here at y equals 0 on the horizontal axis. In other words, the curves are never intersecting the x or y axis. They only approach. That's what an asymptote is. Okay, don't think I have to explain. All right. But you can see by looking at 1 over x, it may give us something important. Where am I going with this? You can see that the 1 over x is decaying, right? It decays slowly, okay? As it goes down, right, you can see that there's a decay. There's a decay, right, as it goes down, right? As it goes down, there's a decay here. So there's a decay factor, right? So you can see the function 1 over a decays slowly. Doesn't go fast, it decays slowly. But the oscillation of sine x, right, forces alternating contributions. Okay. Over here, when we were looking at sine x, right, sine x. Okay, see that each oscillation contributes less net area than the previous one. Okay, so less net area. What do I mean by that? I want you guys to think about, what do I mean less net area? I realize you actually have to have a lot of water when you lecture. What do I mean less net area? What's less net area? What do I mean? It's less net area. Right? Each oscillation contributes less net area than the previous one. What I mean net, I mean subtracting the area. So let's say if you look at the area over here, right? So this one here of y equals sine x, the upper curve here has area 1, okay? That's the positive area. The negative area 2. If I did area 1 minus area 2, geometrically, this would cancel, become 0. Equal and opposite crest and trough annihilation. Okay, so that's 0. Where here, the net area, right? The net area between the two we can say is that the net area between the two is a bit more than the net area between the oscillation function, the periodic function y equals sine x. Okay. So that's important. That's another conceptual way of understanding why this interval converges. Okay. Because the wavelength stays constant. Right? You see the wavelength from a physical apparatus. I'm talking in terms of a scientific perspective, not a mathematical perspective, by the way. So right now I'm talking about, like, by using physical reasoning, how we can get a mathematical problem, how we can figure out if that mathematical problem, how it behaves from physical reasoning. Okay, so right now, right, I'm saying is that by subtracting the two areas for the oscillation, right, or periodic function, there's a cancellation of a node, so it goes to 0. Whilst this function here, its net area is a bit greater than the periodic function. If there's any question on that. Okay, so we can say something very important. The wavelength stays constant. Of course, the wavelength has to stay constant. Wavelength is the distance between two crests and troughs, by the way, right? So two crests and trough, this would be a wavelength. Okay, so this would be a lambda. This would be a lambda. It's crests and troughs, lambdas. Okay, I'm not going to go into detail about that anymore, but I hope you understand what I mean. So wavelength stays constant. Wavelength stays constant. The amplitude of the envelope shrinks. Okay, and the cancellation dominates the accumulation. Again, cancellation will dominate the accumulation of the function, okay? Because obviously, if you have, as you can see, the positive and negative areas, the net area between them by subtracting the two areas would be 0, right? So that plays a bigger role than any accumulation of the curves. Okay, so that's the 3 important things. Wavelength is constant, amplitude of the envelope shrinks, and cancellation is going to dominate over accumulation. So this integral, right, converges because the geometry tells us that. It beats the magnitude. The geometry tells us that the integral will converge. Okay? Any questions? Any questions at all? Please throw something at me. I enjoy having an interesting conversation, especially getting to know my audience of subscribers, or a new subscribers, or a new potential, whoever you are. Right? There's an infinite number of names. All right. Now, how are we going to... so I mentioned all of this. I gave you a really deep, comprehensive understanding of how to conceptually evaluate pretty much an integral or a sum or anything to determine if it converges or diverges without calculating it actually. So this is something that you can put into your mathematical methods toolkit, okay? Especially for those of you taking, calculus ODEs or anything of that nature, or physics too, right? All these things can be applied to physics when you do more advanced physics. Okay. So one last thing that's very important I want to mention is how to decide if, how to decide convergence before calculating anything. Okay, so how do we decide? Okay, so how to decide convergence before calculating, right? So before calculating anything, or calculating anything, and I really mean anything. So how to decide convergence before calculating anything? There's a few characteristics that I want to put in. So you need to ask yourself, okay, so ask yourself the following, okay? Here are the following things I want you to write down, okay? So please write this down. Number one is, does the integral oscillate? Sorry, not integral, integrand. Does the integrand oscillate? The integrand oscillate. That is very important, okay? Number two, okay, so number two, does its envelope decay? So does the envelope, does the envelope decay? That's why I drew two functions, one for sine x and one for 1 over x. Well, the sine x was, part of that integrand was oscillating, and the 1 over x, you can see what's happening to its envelope, right? Its envelope was decaying, okay? So that's very important. Okay, number three is cancellation. Let me use blue, I like to rotate colors. Is cancellation symmetric? Is cancellation, this is very important. Cancellation symmetric? Is it symmetric or not? Okay, so if it's symmetric, then put as check mark, right? Right, and then number four, does the phase increase monotonically? Okay, so 4. All right, so does the phase increase monotonically? Number 4, does the phase, does its phase increase monotonically? Monotonically. Okay. Now, if it's yes to the first three, then you get conditional convergence, right? So you have to be able to know what type of convergence you're getting. It matters. They may ask absolute or convergence, conditional convergence, or whatever. If you get 3 out of the 4, it's conditional convergence. Okay. Okay, so I hope that helps, right? So this checklist actually helps replace memorization, replace guessing, or any of that nonsense, right? And it allows you to actually, right, put in a structural framework, a structural reasoning framework, physical intuition, right, and confidence. Okay, so this checklist is really interesting. So as opposed to just using memorized formulas only, you now have a way, a fast way. It's not always fast, depends if the integrand, to determine if the entire integral will converge and what type of convergence it will be anyways. Okay. Right. So oscillatory integrals are not exceptions. Okay. That's what I want to say. Okay? Oscillatory integrals are not exceptions. Okay. They are the natural language, pretty much, of waves, signals, and the natural science. Okay. So pretty much once students internalize this, actually, you will understand Fourier transforms. They'll make more sense because I showed you the connection between the oscillatory integral and the Fourier transform. Those of you who know Fourier transforms, you automatically see how this is really handy. Okay. So Fourier transforms make sense. Diffraction will feel more natural, right? All right. And convergence itself stops being such a mysterious thing. Like, why are we doing this? Well, and sometimes, why do I need to do a big calculation? Another reason why this is really handy is for 2 reasons. One, it will make you, for those of you who are just interested, maybe you're an undergraduate, but you're not in your classes right now. Maybe you're just learning this yourself, right? As I said, it's a new thing in your mathematical toolkit, a new way of thinking. That's one beneficial thing. But another thing too is that if you're in an exam, and quite often exams have tricky questions, right? And the trick that professors usually do is they'll give you problems to calculate. You know how to calculate them, maybe you do, maybe you don't. But you're given problems and you have to calculate, and they take so long, and you're wasting too much time. If you know tricks to bypass it, then you decrease time, you move faster through the problem, you move faster through the problem, you move faster through the exam, you have more beneficial results. Okay, so knowing this trick should be in all your toolkits for all of you math majors, physics majors, and engineering majors. Okay, this should be like, yeah, your bread and butter for convergence and divergence. Okay. All right. Anything else I need to mention here before I get going? Let's see. Nope, nope, no. I think we're good here. Yeah, I think we're good. So that's going to be it. But before I go, let's pause here. Okay. I need to pause too. Too much talking. Let's see if anyone's coming in now. Sometimes when people come, and that's like not beneficial for me or you guys either. At least who want questions answered right when I'm on. Okay. But I do have to get going. So let's pause here. Okay. All right. I think what we saw tonight was interesting, right? Is that convergence isn't just about size or just using a specific formula. It's about the structure. Okay. It's about the structure. Oscillation creates cancellation. Yes, I'm a bit of a poet. Yeah, oscillation creates cancellation. And once you learn learn to see it, once you learn to see it, oscillatory integrals become stop becoming mysterious, right? So if this session helped and something finally clicked, that's not just luck. Okay. This symmetry first structure first way of thinking is developed deeply and comprehensively in my book, Advanced Integration Techniques, written specifically for undergraduates. Okay. All right. So if you want to build this kind of intuition and the guidance that I'm going to offer, right, in calculus, differential equations, or in physics, I also work one-on-one with students as a coach. Okay. So as a coach/tutor. Okay. So if you want help in your calculus, your differential equations courses, or your physics courses, I can help with one-on-one, coaching. Okay. So the goal isn't to do more calculations if you're stuck on anything conceptual, right? It's to know what kind of problem, okay, you're facing with before you actually use a formula. That's the most important thing, okay? Thanks for thinking seriously about tonight, with me tonight, actually, okay? And I will see you in the next session, all right? Bye for now, guys. It's been good. Take care.